In this lesson, it's finally time to train our model. We're going to model our house prices using a technique called multivariable regression, which is also known as multiple linear regression. But what does that mean? In a previous module, we've been estimating movie revenue based on movie budgets. We were using a simple linear regression model that looked like this. We had one explanatory variable, which were the movie budgets, and we were busy estimating the values of these theta parameters, theta 0 and theta 1. When fitting more than one explanatory variable, more than one feature, the equation for the regression will look like this instead. This is the format of our model for our multivariable regression. Now, we don't have n different terms. We've got 13 features in our dataset, and these are the ones we're going to use. So in fact, when we adapt this generic model to our specific circumstances, our equation will actually look something like this. The estimate of the price is equal to theta 0 plus theta 1 times Rm, plus theta 2 times our second feature, plus theta 3 times our third feature, and so on until we get to our last one. What this equation is telling us is that our estimate of the property price will be a linear combination of these 13 features. So it's still a linear model. Okay, so this is the model for our regression that we will be fitting our data to. And when we run our Python code, we'll get a value for each of these theta parameters that we see here. These are going to be our coefficients that we're interested in. But before we write our code and run the numbers, did you ever wonder why this technique was called regression in the first place? Where does this name regression actually come from? I mean, regression is such a strange word to be using for fitting a line to our data, right? So this technique and the name actually go back a long, long time to an English gentleman called Francis Galton. Sir Francis Galton, in fact. Sir Galton lived in Victorian England and had quite a few talents. One of the many things he's remembered for today is his invention of the Galton board. Yep, he named this invention after himself. Anyhow, a Galton board is basically what you end up with if you were to take a Japanese pachinko machine and then extract all the fun out of it. The Galton board is a contraption that has a bunch of balls and pins in it. When you turn this board upside down, the balls go through a single opening at the top, and then they start bouncing off the pins. And here's the fascinating part. What you end up with at the bottom of the board will look something like a histogram from Matplotlib. In fact, you get a very particular type of arrangement in the slots at the bottom. And if you squint a little bit, you'll actually recognize our old friend, the normal distribution. Most of the balls end up in the middle, but a very, very few balls bounce around like crazy on these pins, and they end up on the sides of the board. They end up as outliers on the very, very left or on the very, very right-hand edge. Now, needless to say, a lot of statisticians at the time were very excited about this invention. But the thing is, Sir Francis Galton was not a one-trick pony. No, sir. Being quite interested in both distributions and outliers, he looked very, very, very carefully at the sizes of things. From the sizes of the seeds of his sweet peas to the sizes of people. In particular, he was very, very interested in how size changes from one generation to the next, especially with regards to outliers. Now, one thing that Sir Galton noticed was that when you had a very, very tall father, and that father had a son, and that son grew up to be an adult, the adult son was usually shorter than his father. Sir Galton called this phenomenon regression to the mean. That's where we get that word from, regression. Now, you can even observe this phenomenon of the regression to the mean in, say, like the NBA. Professional basketball players tend to be very, very tall, right? For example, Shaquille O'Neal was 7'1" or 216 centimeters. At least that's what he's listed at on Wikipedia. But what about the sons of an NBA player? Shaquille O'Neal's son, Sharif O'Neal, is slightly shorter than his father at 2 meters and 8 centimeters, or 6'10". Another example is actually Michael Jordan, who was listed at 6'6". And Michael Jordan's son, Jeffrey Jordan, is listed at 6'1". Now, I realize those are just 2 examples, and there aren't that many sons of basketball players in the NBA whose height you can pull up on Wikipedia. But you'll find that this pattern holds on average. The NBA players' sons will end up shorter than their dads on average. This is regression to the mean in action.